Okay, so I am going to get to this, find some examples. And it looks like Natasha has joined. So, hi Natasha, we are going to go over the difference quotient. I am just looking for some examples so that I don't make up something that ends up being really gross. Which unfortunately happens a lot with algebras if you're not careful. Okay. So this is going to, let's see, so we've got f of x equals 5x minus x squared. And we want to find the difference quotient, which is f of 5 plus h minus f of 5 over h. And so I will label this that this is the difference quotient. And so I kind of wanted to explain what the difference quotient is so that you have an idea of what exactly is going on here. So I'm going to just draw a graph, and I'm going to label 5 because one of our values here is f of 5, so that means an x value of 5. And then we have f of 5 plus h. So we just have some little section here, some difference from 5 and then another number, so that's 5 plus h. So we're just adding a little bit on to 5. So what the difference quotient is, it says you have some sort of graph. Okay, I don't actually want it to go through 5. So yeah, I'm just kind of making up a graph. So I'm trying to do the graph that we're given. I know it's going to be a quadratic and upside down, but not perfect. But basically what the difference quotient is saying is we are looking for the difference between, maybe I shouldn't do it in that color. Let's do green. So we've got the function value, the value of y at 5 plus h, and then the value at 5. So f of whatever that is y. So we're looking at the y values here. And so we got y. So this is basically y. If you can think of it as y1 because it's the first one if you're going from left to right with the x. And y2. Basically what we're doing here is we're finding the slope. The difference quotient is the slope, where your second point is a little bit beyond 5, and then your first point is 5. And then the difference between, if you're looking at your, if we do x2 minus x1, or x2 is 5 plus h, and then we're subtracting 5, the 5's cancel, and that's how we end up with h in the denominator. So the difference quotient is actually just the slope formula between 2 points on something that's not a line. So because it's not a line, we don't call it the slope, we call it the difference quotient. Because you can, but you're just basically finding the slope between 2 points, and we're just approximating it by a line. So if I connected those 2 points, it's a really bad drawing, but you could make a line between those 2 points. The whole point of the difference quotient is that you can do it with any value of h. So I could add 1, and so I would do it between like 5 and 6 if I added 1 as my h. If h is 2, it would be between 5 and 7. Ideally, when we get to calculus, you're looking at very small values of h so that you can find the slope at 1 point, at the exact point, or as close to 1 point as you can get instead of like looking at a wide range. So calculus looks at very, very small values of h. What we're going to do is just show you the algebra to calculate this without worrying about what h is. H could be anything. We're just going to use the, just do algebra to simplify this. And then when you get to calculus, you'll learn what that means and you'll learn all the shortcuts to do it. So the difference quotient is basically just find the slope between 2 points, one of them which has an x value of 5 in this case, The other one has an x value of 5 plus h. So now that I've explained what the difference quotient is, we want to actually calculate it. So what I recommend doing is these function values is I would work them out separately. And so I like to color code. And so let's say we first want to find f of 5 plus h. So I'm going to do that in yellow. So I'll just do that over here. So f of 5 plus h. So our function value, or our original function, we have x, and I'm just highlighting x. So everywhere that I have something in x, I'm now replacing that with 5 plus h, because that's inside the parentheses. So instead of 5x, I now have 5 times 5 plus h. That was what was in parentheses. And then oops, I wanted the black, minus, and then instead of x, it's 5 plus h. So the reason why we use function notation is so that you can indicate that we're just going to replace x with 5 plus h in this case. So now we want to follow all of the order of operations to simplify the right side. So first is I can, let's make this a slightly little lighter. I can use orange. So I want to distribute my 5 through the first set of parentheses here. So first I have 5 times 5, which is 25. And then 5 times h gives me 5h. Now I have this 5 plus h squared. So what helps a lot of people is to actually write that out so that you can use FOIL. If you have the shortcut memorized for getting that, for squaring that value, that's fine. Most people don't at this point, so it's to your benefit to write it twice so that you can go through the FOIL process. And I put brackets around it because I want to make sure that that negative stays out of it, because we're going to FOIL and then we subtract everything we FOILed. So when I FOIL, I'm going to first do the 5 times 5. So I'm going to go here, 25 plus 5h minus, and then in my brackets, 5 times 5 is 25. And then I multiply the outsides, which is 5 plus h. So that's, or 5 times h, which is plus 5h. And then I multiply the insides. H times 5 is another 5 times h. And then h times h gives you h squared. So I FOILed that out. Now I want to distribute the negative sign outside of the brackets. Or if you want, you can simplify the brackets first. I'm going to just distribute the negative sign as my first step. So I have 25 plus 5h. And then I'm going to distribute the negative, which gives me a negative 25 and a negative 5h, another negative 5h, and a negative h squared. So I'm just multiplying everything by this negative sign. And since they are all positive, they now all become negative. So now I want to simplify. So if we look at it, I have a 25 minus 25, those cancel out. I have a 5h minus 5h, those cancel out. And so I'm left with minus 5h minus h squared. So f of 5 plus h is equal to negative 5h minus h squared. So I'm going to just highlight that for now. And before I move on, are there any questions of how I simplified the right side or what I did there? Okay. So now I'm going to go back up here. So I just did the f of 5 plus h thing. Now let's do f of 5. So I'm going to do that over here. I should have enough room. F of 5. So now everywhere that I see x, I'm going to replace it with 5. So I have 5 times 5 minus 5 squared. So Natasha, yes, should you show all of this for the homework? So on the homework, there is no difference quotient problem, so you won't have to do this on the homework. This shouldn't be showing up on anything other than like it might be on a quiz. But if it's on a quiz, just show what you can, enough that you can figure out the answer. It's more important on a quiz, to have the work if maybe you got it wrong, but if you got it right, it doesn't matter as much. But for the homework, at least, this won't be on the homework. So just like before, I had everything that was an x has now been replaced with 5, and now I want to simplify on the right side. So 5 times 5 is 25, minus, and then 5 squared is 25 again, and we end up with 0. So f of 5 is equal to 0. So now that I've figured those out, I'm going to rewrite my difference quotient. So I'm going to go back down, and first I'm going to write what the difference quotient is again. So it's f of 5 plus h minus f of 5 over h. Now I'm going to replace my function values. So I'm going to replace f of 5 plus h with what it's equal to, negative 5h minus h squared. And so I'm going to highlight that. So I'm replacing that. Then the next part is f of 5, which we found is 0. So I'm going to be replacing that with 0. And I'm going to actually write it out. Sometimes that comes out to a number and it doesn't just come out to 0. But this is what we have so far. We have negative 5h minus h squared, then minus 0 over h. And so now what we want to do with the difference quotient is you're simplifying. So we're not solving anything. I just want to keep going to the right, or simplifying on the right side if I want. And if you want, you can just write this as difference quotient so you don't get tempted to do anything on the left side. So, of course, minus 0 is nothing. So I can just rewrite this as negative 5h minus h squared over h. Now, I'm going to actually rewrite this so that the h squared is first, because we like to have our highest exponent first. And because it's a negative h squared, it's still going to be a negative h squared. So I'm just going to rewrite this. So what we have here is a rational expression, which we looked at in week 1. And we need to factor the denominator so that we can cancel things out. So I can factor out let's factor out an h. Usually factor out a negative because the first part is negative. So I can factor out a negative there. Negative h, which will leave me with an h minus 5. If I factor that out, or h plus 5 because I factored out a negative. And then I have an h in the denominator. So now I can cancel these h's out, because there's one on top and one on the bottom, which leaves me with a negative h minus 5. Or if you want, you can multiply that negative through to get negative h plus 5. Oh, never mind, that still isn't h minus 5. I actually switched my sign again. That should be a plus 5 right there. and then you multiply, you get negative h minus 5. And so that is a result of the difference quotient. And so you can think of that as like this, it's basically an equation to get the slope at some point h. So it gives you it's sort of an expression or a way to find the slope, and then you just plug in how far away from 5 you want to be. So if I go back to my graph here, I kind of zoom in. So let's say I wanted to let's say I wanted to be at 6. And so this difference here is h equals 1. And so I want to know, okay, what would be basically the slope of the line between 5 and 6, or the slope of the graph. So let's say I'm going to just erase these points, and let's say this is what my graph looks like. And at 5 we're up here, at 6 we're down here. And if I was to connect those with a line, I can actually, you can be all fancy and actually make a straight line there. I think I can. So if I was to put a line through those points, you see that the line isn't perfect for the graph, but this formula that we just found will give me the slope of that line if we connected those 2 points. So we just found that m is negative h minus 5. So if h is 1, then the slope of this line that we've just found between those 2 points is negative 1 minus 5, and the slope will be negative 6. So if I had this on an actual graph and it was to scale and all of that, you'll actually be able to see that that's what that is. So that's what the difference quotient means. It's basically giving you a formula so that you can find the slope between any 2 points and draw a line between them, if that makes any sense there. I think I'm going to actually do this in Desmo so you can get kind of a better idea. Because then you can actually see it to scale. So our original functions, f of x equals, zoom out here, 5x minus x squared. Okay. And our difference quotient, we're using f of 5, which is 0, as I found. So I'm going to actually make that an ordered pair so I can label that. And let's just say this is f of 5. Our difference quotient is also using f of h. So that would be an input of 5 plus h, or f of 5 plus h. And I'm going to add a slider for h, so that just means I can change where h is. So I'm going to just label this f of 5 plus h. So right now h is 0, so they're the same point. And then you can see if h moves, if we have that difference, that moves here. Okay, so when I had h equal to 1, that gives us this right here. And it is basically giving us the slope. We saw that formula is giving us the slope between if I connected these by a line. So now what I'm going to do is I'm going to just take a screenshot so I can draw on it. So we know the slope is rise over run. So in this case, the rise is actually a fall. We're going down and then over. So our change in y here, we started at 0, we went to 6, is negative 6. And then we went from 5 to 6, so our change in x is 1, because we only added 1 there. So you can see that what we got by the formula, we got -6, and if you use the slope formula here, you get -6/1, you also get -6. So you can see visually that that formula basically gave us the slope if we had, if we drew a line, and again, I'm gonna have to like kind of eyeball these, but if you drew a line between those 2 points, that basically is finding the slope between those 2 points. So that's what the difference quotient does. And then the whole reason that you're seeing it in this class is because a lot of people have to go to calculus, and actually calculus is the study of rate of change, which is basically slope on things that are not linear. So this is something that follows into calculus, and it's all about how things change, which most things in real life change. Very few things in real life are constant, so calculus shows up all the time in the world. So this is just this whole difference quotient thing is just, we're doing the algebra behind it because we don't want you guys to do calculus at this point. Obviously, you're not in calculus, but it's a concept that's actually used a lot once you get to higher levels of math, and a lot in engineering and meteorology. Any kind of science, anything that has a little bit of science or any kind of science usually ends up doing something like this. So that's what this is. And then the difference quotient is basically just an exercise in doing the algebra, understanding the function notation, being able to plug things in, being able to FOIL, multiply things out, add your like terms, simplify expressions. It basically has like everything that you need to do in algebra in this one problem. Are there any questions? Did that make sense? Hopefully that made sense. I think I did a pretty good job with my hand-drawn picture compared to Desmos. Whoops, I'm still in the drawing. I go to real Desmos. It's not perfect, but it has the right shape. So it was like, I feel like I definitely didn't have it perfect. I didn't have my f of 5 in the right spot, but. Well, I'm assuming that you guys don't have any more questions on the difference quotient. What other things do you need some help on? Or need to see worked out or explanations for?
I am struggling with find the domain for the function of composition where the fog x equals f.
Those are, yes, finding domain of those. Those are very, very tricky. All right. So domains of function composition. And these, I usually have to think through these very slowly to make sure that I'm thinking through it correctly, because it's not necessarily intuitive. So just to go over some notation here, you can see f of g of x, and that is the same as f, and that is not the letter O. It is an open circle, and we read that as f compose g, so it's not the letter O. And then if you have g, where you're plugging f of x into it, it's g compose f. So it does look like fog or goth, but it's not the letter O, it's different. So the book basically has has a picture where they're kind of explaining the domain of f and g and how this all works out. So let's say I'm gonna try to draw their picture. So we've got, let's look at f compose g. We're plugging g into x. So we have something that's g of x, and we have our inputs into g of x. So we can plug things into g of x, and we plug things in, and then we get an output. So these give us some output over here. So let's say our output then comes out of g of x. So we're plugging in x, and out comes g of x, some y value. Then, with a function composition, your g of x is now the input into f. So you take your y values from g of x, your outputs of g, now you're plugging them into f. So now you now have f of g of x, because you're taking what you got out and plugging it into a new function. So when you're thinking about the domain of f of g of x, we have to think about the domain of x and the domain of g of x, because both of those are inputs. So domain is all about the inputs. And so the domain is the input. And so we need to think about the original inputs x, but then we also need to think about what we're plugging into f, which is now our outputs, g of x. They both matter, because some numbers I can plug into the first part, but maybe I won't be able to plug into the second part. So I'm trying to find in the book, see if they have a good way to explain beyond their picture there. Yeah, the book's not really doing a great job with this. So let me take some of their examples and kind of show it. So they have f of x equal to x squared minus 9, and g of x equals to the square root of 9 minus x squared. So we're doing f of g of x. We're plugging g of x into f, or f compose g. So when you want to figure out the domain, you first need to start with the domain of the first function, g of x in this case. So first we need the domain of g of x. So for a square root function, we can't put negatives into a square root, because then you get imaginary numbers, and we can't graph imaginary numbers, because functions are things that we can graph. They have an input and output. So if they're going to get imaginary numbers, then that's not something that you can really graph. So our inside of inside the square root needs to be 0 or positive. So I'm going to take the inside of the square root, which is 9 minus x squared. That needs to be greater than or equal to 0. So now this is one of our, this actually comes back to the polynomial inequalities. This factors, so I'm going to just write the factored form there. We have 3 minus x and 3 plus x. And if you want to know where it's equal to 0, you set each of those equal to 0. So we get 3 is equal to x, and then 3 plus x equals 0, so x is equal to negative 3. So in order to find the domain, I'm going to have to do one of these polynomial inequalities here and make the sign chart. So I'm going to put -3 and 3, and this is on my number line for x. Now, this is greater than or equal to, so I can include my 0. So I'm going to draw solid lines here because it's greater than or equal to, so those zeros are included. And I'm going to take my 3 minus x, my 3 plus x, and then we're looking for the multiplication here. And I want to plug numbers in each of these intervals. So my interval to the left of -3, let's say I plug in -4. So if I plug -4 into 3 minus x, that's 3 minus -4, so that's 3 plus 4, which is 7, so I get a positive. If I plug x into, or the -4 into x for 3 plus x, that's 3 plus -4. That gets me -1, so that's a negative. And a positive times a negative is a negative. Now between -3 and 3, I can plug in 0. And so if you plug in x equals 0, you get 3, which is positive, 3, which is positive, and a positive times a positive is a positive. And then I want something larger than 3 in the next interval, so I can pick 4. So if x is 4, 3 minus 4 is -1, so that's a negative. 3 plus 4 is 7, so that's positive. Negative times a positive is a negative. So then I go back and I want greater than or equal to 0, which is the positive. So I want this part of the number line because that's where I have positive signs. So this is all to get me my domain. So my domain is -3 to 3. And we can include the endpoints because it's an equal to 0 part, because it's greater than or equal to. So we did all that. We found our domain. So that's the domain of g of x. So now what happens is, so that's what we're plugging in, and now we're getting outputs. So when we have that, what are our y values that we get out? What is the range? What do we get out from here? So that's the second part. So I just found my first part, my first little mushy symbol here. I don't even know, like the little thing. So now I want to find what the output is and to find those numbers because those are going to be the input to the next one. So next is the range of g of x. Because that is your outputs. Now, generally, when I find the range, I just do it by graphing because it's a lot harder to find than by doing the domain. So I'm going to pull up Desmos, and I am going to just graph our g of x function. And that is square root of 9 minus x squared. Okay. So this is what we get when you graph that function. So every input has one output, and you can see our domain. We have -3 to 3. You can see that. So now we can say what the range is. Our y values, our range is from 0 to 3, it looks like. So 3 is up here. So the y values are only between 0 and 3. So that is going to be our range. So I'm going to just copy down the graph. So it looked like this, -3 to 3. And then, so our range is this part of the graph. And so that is from 0 to 3. So now that is the input into the next function. And so this is, so we just found our output here, and now we're looking at that is going into f. So our output goes into f, that's the next part. So we found our domain. Now we found our range. And so now 3 is, first we need to find the domain of f of x, because we need to figure out what are we allowed to plug into there. And then we need to see if our range works for that. So f of x is x squared minus 9. So x squared minus 9 is a quadratic function, and the domain of quadratic functions is always all real numbers. So f of x is quadratic, and the domain is all real numbers. So that's negative infinity to positive infinity. So that is good. So that actually makes things easy for us. So we know the domain of f of x, all real numbers. So once you find the domain, then you say, is there any, you ask yourself, is there anything from the range of g of x that is not in the domain of f of x? So the question is, my output that I got from the first function, am I allowed to do all of those numbers work in the domain in the next one, or are there things that don't work? If the whole range of x is in the domain of f, so if the range of g of x is contained in the domain of f of x, so if there's overlap there, that's basically what it means. If those overlap, then the domain of the composition of f composed g, which is what we're finding here, is the domain of g. So let me break this down. Okay, so g of x, our output, is 0 to 3. And for f, we're allowed to put in any number, because the domain is all real numbers. So that means that what we get out from g of x is allowed to go into f. We have no issues there, because f allows any number to go inside. So because of that, the domain of our composition is the domain of the first function, negative 3 to 3. And so that gives us an answer of this case. F of x domain is, and my pen won't draw, let's try this again, is, there we go, negative 3 to 3. Now the question is, what happens if you can't plug in all those numbers? You know, what if you have some issues there? What if f is something else and it doesn't allow every number? So let's take a look at that situation. And I'm not sure why all of a sudden I've lost like half my screen here. So what if f of x is 1 over x? And we want the domain of f of g. So g has not changed. I'm going to use the same g that I had all the way up here, where the domain is from negative 3 to 3 and the output is 0 to 3. But what's changed is f of x. So we don't have to redo steps 1 and 2, but we do need to redo step 3. So step 3, we want to find the domain of f of x. So in this case, f of x is 1 over x, and whenever you have a rational function like this, where you have x in the denominator, we have to be careful because we can't divide by 0 and that denominator is dividing. So that means whatever is in the denominator cannot be 0. So this tells us that x cannot be equal to 0. So our domain is saying that x is not equal to 0, but we can have anything else. So everything else is fine. Okay, so now let's look at step 4 again. Is there anything from the range of g of x that is not in the domain of f of x? So here's where we have something different here. Because our range of g of x doesn't include 0, or our domain of f of x does not include 0, but our range of g of x does. So we have something in the range of g of x that we cannot plug into the next thing, 0. We can't plug 0 in because f won't allow that. So since my input to f can't be 0, this tells me that my g of x cannot be 0. Whatever my output is not allowed to be 0. Because if g of x is 0, I can't plug it into f because f is not allowed to have an input of 0. So we're kind of working backwards here. So we're looking at that domain of f. We've got an issue here. So I need to say, okay, g of x can't be 0, so then I need to find out what value makes g of x equal to 0. What is our issue here? So then you go back and you replace g of x with your function, square root of 9 minus x squared. Square root of 9 minus x squared. So that is not allowed to be 0. So this takes us back to our original domain. Our domain originally was where we could have the inside of the square root greater than or equal to 0. But we can't have this equal to 0 because the square root of 0 is 0. So now we have 9 minus x squared greater than 0. So we're not allowed to include 0 here because 0 gives us a problem when we then plug into f of x. So we go back to my sign chart here, and normally we're allowed to have our endpoints -3 and 3 allowed to plug those in. But because now those will cause us problems in f, we are not allowed to plug those numbers in. And so instead of our domain being brackets at -3 to 3, our new domain is now going to have parentheses. So our new domain of f composed g will be parentheses -3 to 3. So once we figured out what f is not allowed to have, we now have to work our way backwards to figure out what values for the first, where we started, we can't plug in that will down the line cause issues. Hopefully that wasn't too confusing. You've got like a chain of logic that we're kind of following here. That you're basically going to this picture and you work your way this way, figure out what's not allowed, and then work your way back to see if that kind of excludes anything. Some people, what they like to do is start here and only go backwards and then work their way. And that's something that you can do as well. So you can go either way. You can work from here and go backwards. But that's sort of the logical thinking process that you have to do when you're figuring out a domain and range for function compositions. It's not like an easy kind of thing because you have to consider, what am I plugging in? Am I allowed to plug that in? What is the output? Will that output cause me problems in the next function? So there's a lot to think of. It's very, very process and like logic oriented here. And this is why I generally don't ask questions about function composition on like quizzes or in assignments, because it's a lot of thinking to kind of work your way through the whole logic of it. So, did I lose you guys? Do you have any questions on that? I could try to do it the other way, or I could just say, okay, what if we wanted to find the domain of G of F to show you how, because the order there matters. What you're plugging in first and second, it changes what the domain is going to be. Just like the actual function composition, the output will be different based off of what function's getting plugged into what other function. So I could do G of F and show you that. Yes, no, don't care, have other questions?
That would be good. I mean, it's a lot to take in, and it is a little confusing, not confusing, but it's very difficult, because that's where I got lost at, trying to put the logic behind it.
Yeah, this is why I do this very slowly myself, because it is a lot of logic. Okay, oh, and now I don't know why like half the screen is just I'm gonna try closing it and then closing that back up, or opening it back up and see if that will pop back up, because if I'm losing half my screen, I don't know what is going on here. Maybe if I just open a Word document, I won't lose that, and I could just do it in Word instead. Okay. Nope, Word's doing the same thing. But I think I know how to fix it in Word. There. There's a trick. I have this happen to me in Word a lot, and I don't know why. Okay. So let's go back to the very first example where f of x is, where I didn't change f of x. What was it originally? X squared minus 9. And let's say g of x is square root of 9 minus x squared. So one way that you might find this easy is to first identify the domain and range for each of these separately. So I'm going to use D for the domain and R for the range. So we've already gone through the work. We know that the domain is all real numbers for f because it's a quadratic. And also quadratic equations, their range, well, that it does actually. I was going to say it's all real numbers, but it's not, because I don't know what I was thinking. So we'll let the range sit there. We did find the domain is -3 to 3 for g of x, and then we found the range was 0 to 3. And if you want to see that in just regular inequalities, I can write it like that. Okay, so now let's graph our f of x, x squared minus 9, so we can get the range. And you can actually find the domain this way too. So f of x is x squared minus 9. Okay, so I'm going to have to zoom out. So our range, our low point here is at minus 9, and then it goes up forever towards infinity. So our output values, if we're looking at our y values, are -9 to infinity. So that is the range. So it includes -9. So -9 to infinity. Or if you want to write that as an inequality, it's x is greater than or equal to -9. So your first step, if you want, is just to find the domain and range of both functions. So we have done f of g of x. Now let's do g of f of x, so you can see how that changes things. So g of f of x, or g compose f. So we have x values, we are plugging those into our function for g, and then those values are getting plugged into, whoops, I did it backwards, function of f, and then those values are being plugged into our function for g. So our x gets put into f, those outputs get put into g. So that means, if another way to think about it is that the range of f needs to be equal to the domain of g, or these need to be connected in some way, because my output of f is going into g. So notice that our range of f says that x is greater than or equal to -9, but we can only plug in values between -3 and 3. So there are some issues there. So I'm going to just kind of draw this on a number line so that you can visualize this. So let's say I have a number line of x. I'm going to put 0. I'm going to put -3 and 3. And I'm actually going to make this a little longer so that I can just put -9 on here. So let's say my range, my output, actually I said this should say y is greater than or equal to -9, but that is their input to the next one, so that will be like an x. So that's greater than or equal to -9. So if I highlight, this part of the graph is my output in terms of just numbers, if you ignore the x or the y. So that's the output, or the range, which is now going to be the input into the domain. So the domain of g here is from -3 to 3. So I'm going to highlight those. Okay, I expected that to be overlapping, and it went behind it instead of, there we go, really dark, but so that is the portion that we're allowed. So this area is allowed to be input to g, but everything in green here is output from x, from f. So we're getting more values as outputs than we are allowed to plug into g. We have some issues there. So we're only allowed to plug in the values from -3 to 3, because that is our gain for g of x here. So because we're plugging f of x in to g, you can think of it as this part right here is now f of x. So our f of x has to be between -3 and 3. That output there has to be between there in order for it to fit into g of x. So I'm going to write this. So our domain of g of x is -3 to 3, but f is getting plugged into g of x, So I can replace x with f of x because that's what's being plugged in. Now I'm going to go back and replace f of x here with our x squared minus 9. And this will allow us to work backwards so that we can find out what values in the domain of f of x we're allowed to plug in. That will work its way through here and follow the chain so that it will eventually work out. So this is a type of thing that we have not solved. We have not solved inequalities in this form where you have things on both sides. So this is something new. When you have compound inequalities like this and it's an x squared, we've only done these with linear. This is, you can think of this as this and then your x squared minus 9 needs to be less than or equal to 3. So it's like you have two separate things that you're solving here. So where is our x squared minus 9 greater than or equal to negative 3, and where is it less than or equal to 3? For what values of x make that true? So again, oops, these are polynomial inequalities. And when we're solving polynomial inequalities, we want them to be 0 on one side. So I wish I had picked things that were not quadratic because these are very lengthy problems. If I add 3 to both sides, we get this x squared minus 6. And this is going to actually cause problems because this is not factorable. If you get something that's not factorable, it's actually easier to just pretend that it's an equal sign so that you can find those endpoints for when you do the sign chart. Because otherwise it's going to be gross. So if I'm just solving and pretending it's an equal sign, I need to take the square root of both sides. And so I'm going to get plus or minus the square root of 6 equal to x. And that's what I'm going to make the sign chart from. And I'm going to have, let's see, 9, 10, I'm going to have the same problem on the right. That's going to give me something that's not factorable. So I'll just pretend it's equal to 3 for now and solve for x squared. So that gives me x squared equals 12. When I add 9 to both sides, I take the square root of both sides, and I get x is equal to plus or minus 12, which actually is plus or minus 2 square root of 3 if you want to simplify that. And then again, we have to make a sign chart for here as well because we're going to have multiple things that are going to be excluded. And next time I get asked to do a problem like this, I'm going to have to pick simpler problems. I need to add another page. Okay. So let's do the one on the left here to make the sign chart for that. So we were originally negative 3 is less than or equal to x squared minus 9, which is 0 less than or equal to x squared minus 6. And we usually write this with the x part on the left. And then when you flip them, you have to flip your inequality symbol as well. So we're looking for where this is greater than or equal to 0. So I'm going to make my sign chart. And we had negative square root of 6 and positive square root of 6 on my sign chart. Because it's greater than or equal sign, I am allowed to include the endpoints. And how I'm going to check my sign chart is I'm going to have x minus the square root of 6 and then x plus the square root of 6. So that's what I'm going to use for my things in the sign chart and then multiplying those together. For filling this out, I would probably recommend just using a calculator. The square root of 6 is 2.4, so if I can plug in like -3 and +3 on either side, and then I can plug in 0 to make my sign chart. So I'm going to just plug those into x, and then I'm going to write down whether my numbers are positive or negative. So I'm going to get a negative here. I still get a negative here. Negative times a negative is a positive. If I plug in 0, that's negative, positive. Those multiply to a negative. And then this comes out to a positive. This is a positive, and those are a positive. And then we want greater than or equal to 0. So we've got two sections here. So we've got -infinity to negative square root of 6. And then we're combining this, so it's a union symbol with square root of 6 to infinity. Okay, now I have to do a sign chart for this other one, where I have basically the square root of 12 on either end. So that was x squared minus 3 less than or equal to 3. Or x squared minus 9 less than or equal to 3, which became x squared less than or equal to, so minus 12 less than or equal to 0. And if that's in the correct form, so now we're going to be looking at negatives when we make our sign chart. And we'll just use x minus the square root of 12, x plus the square root of 12. I'm going to put those on my number line here. And then again, we're looking for where the multiplication here. I still have the equal to symbol. And my calculator, square root of 12 is 3.4, so I can plug in x equals -4 or x equals 4 and x equals 0 to make sure I'm in each section. Now I'm just going to do all of this on my calculator, so it's going to be a negative times negative is a positive. When I plug in 0, that's negative, positive, which is a negative. And then positive. This is positive, which is positive. Okay, we're looking for less than 0, so in this case, we want this area. And so we've got from negative square root of 12 to the square root of 12, which then I can simplify if I want. So I kind of rushed through the sign chart thing just because this is getting lengthy. Okay, so going back to this whole point. So we want the values of x where both of these things, where there is overlap between these two answers. So we're looking for the overlap between what I have on the first sign chart and the second chart. We're looking for the overlap because that's the and that I have here. And if you've kind of got lost in what we were doing, all of this was so we could figure out what x values we can plug in so that they work for the output, so that they work into the input into G. So I will overlap these two intervals. So what I'm going to do is make another number line. And we've got the square root of 6 which is about 2.45, and then the square root of 12. And I'm doing these so I know where to put these on my number line, is 3.46. So I had negative square root of 12, negative square root of 6. I'm going to just put 0 on there, square root of 6, and square root of 12. And I'm looking for the overlap. So my first sign chart gave me an answer of this, these two intervals. So I'm going to highlight those two intervals. Left, negative square root of 6, and right, a positive square root of 6. So left and right. This sign chart gave me between negative 12, or negative square root of 12 and square root of 12. So that's here. We want the overlap between those intervals. So you can see with my highlighting that the overlap, now that doesn't want to draw, is right here and right here. And that is our final answer for the x values that we are allowed to plug in. So this gives us domain of g of f. We've got negative square root of 12 to negative square root of 6. And then we have the union symbol to combine these, and then square root of 6, and then square root of 12. And had I known that we were going to go into this deep, I would have picked much easier problems to work with because this is quite the lengthy process. Did I lose you? Are you now worse off than you were?
It's just a lot to take in. I have to rewrite my notes, so maybe that will help.
Yeah. You may want to rewatch this multiple times to kind of follow the process. And I'm going to make a note for myself that for when I teach this next term, that I'm going to spend time to come up with an easier example than just picking problems from the text like this. Because it can get very, very convoluted. And maybe if I can figure out a way to kind of write like a step-by-step or sort of like go through the logic behind it, that might be helpful. I think this is we've done a lot today, so I think this is about as far as we should go. I did just make a note for myself, and maybe I will probably have some free time tomorrow after I grade your discussion, so I might try to come up with a different video, or make a video with easier problems so that this is not so convoluted, and see if that helps. So thank you guys for sticking with me for that. I really appreciate it. Don't worry too much about this kind of things because we pretty much try to stick for domain and range, not on compositions, because they can get a little confusing. So we try to avoid those. Because it is, and the difference quotient. So both the things that we covered tonight, we try not to quiz on because they take a lot of time, as you have seen. So, I mean, that makes you feel any better about how you've just spent your Thursday night. But I do appreciate you guys sticking with me, and I will send this out tomorrow and then also see about filming or writing a different example with some easier things to work with, things that don't come out to nasty square roots, and see if that will make more sense. So,
thank you. I appreciate you doing that.
yeah, you guys take care and stay safe, and I will talk to you guys later. Bye.